Okay, guys, how are you doing? In this session, we're gonna learn about series resistors in voltage division, also a parallel resistors in current division. So let's begin from the series resistors. The equivalent resistors of any number of resistors connected in series is the sum of the individual resistance. So elements are said to be connected in series when they are connected end to end like this, cascaded into end, where any other branch without any other branch crossing between them. So when they are connected end to end or cascaded like this, uh, they are said to be in series. So the equivalent resistors of the equivalent or the combined resistance of resistors connected in series is simply their summation of individual, the summation of the individual resistors. So this formula is simply derived by applying uh, KVL to this circuit. This circuit is a single loop circuit, so we can apply KVL into the whole of this circuit, as you see. So when we apply KVL, so we're gonna add the individual voltage. So the supply voltage is this one. The supply voltage is equal to V is equal to V1 plus V2 plus V3 up to Vn. So we know that from the previous section, elements which are connected in series share common current. So when elements are in series, they have the same current. So V1 means I times R1, V2 also I times R2, V3 I times R3. So I is common for their whole. Also we assume these resistors as are equivalent. So when we assume as are equivalent, V means I times R equivalent because they are the same loop. V is I is equal to I times R equivalent. So we take I common from these resistors. So also cancelling I from both side, dividing both side by I, by the common I. So R equivalent will be R1 plus R2 plus R3 up to Rn. This is how the formula is derived. The second concept is about the voltage division. A source voltage is divided among the resistance in direct proportion to their resistance. The larger the resistor, the larger the resistance, the larger the voltage drop across that resistor. For example, if you have these two resistors, so the voltage supplied by this is shared among these two, dropped among these two resistors. So in accordance to the value of their resistance. The higher the resistance, the larger the voltage drop across that resistance. The lower the resistance, also the lower the voltage drop across that resistor. So as you see, V1 is the V1, the amount of voltage dropped across R1. So it is calculated by V1 is equal to R1, the resistance value of the resistor, over the sum of the resistors in the loop or the circuit. R1 plus R2. For this circuit, we have 2. If you have 3 resistor, we're gonna add those 3 times the voltage supplied, the supply voltage. So this is the share of the V1, the share of the voltage or the voltage drop across the R1. For R2, for V2 also, V2 R2 over R1 plus R2 times the supply voltage. So multiplied by the supplied voltage. This is how we can calculate the voltage division or it is known by principle of voltage division. So it helps us to determine the voltage drop across the resistors, the individual resistors. So we're gonna solve more problem on this on the next session, on the problem solving section. For n resistors, if you have n resistors like this, if you have n resistors like this, so the voltage drop across the Rn's element is calculated by Vn. The Vn is calculated by Rn over R1 plus R2 plus R3 plus up to Rn, the summation of or the equivalent resistance times the supply voltage multiplied by the supply voltage. This is how we can calculate the voltage drop across nth element. So let's head to parallel resistors. So elements are said to be connected in parallel when they share the same two nodes, like this. When they share the same two nodes, so elements are connected in parallel when they share the same two nodes. So elements which are connected in parallel have the same voltages. Elements in series have the same currents. Elements in parallel have the same voltages. So up to nth resistor, the voltage drop across is the same. So the voltage drop across the whole is V. The voltage, they share the same supply voltage because there is no series component or there is no any other element connected in series with the source. So all are connected, all branches are connected in parallel with the source. So they have the same voltage as the source. So when elements are connected in this way, so their equivalent resistance is calculated by the multiplication of, if there are two, if we have two, if you have only two resistors connected in parallel, their equivalent resistance is the product of the resistor divided by their sum. So this formula is derived from this one. As you see, it's the formula is derived by applying Kirchhoff's current law. So Kirchhoff current law to this circuit. As you see, we know that from Kirchhoff's current law, current in a closed system, the current sources or the current in each branch can be added when they are in parallel, like this. When they are set in parallel in the circuit, so we can add their summation. The summation of the currents in the whole system is 0. So their summation, as you see, this is IT come out of the supply voltage. So this all I1, I2, I3, and up to IN is their summation is equal to IT. IT is divided into these whole branches, up to IN. So IT is equal to I1 plus I2 plus I3 up to IN. This is KCL, or their summation. If we take I2 to this side, their summation is 0. KCL says like that. So IT means we assume from this point up to this point as R equivalent. The R equivalent, let's say we get the R equivalent. So IT means V over R equivalent. The voltage, the supply voltage divided by their equivalent voltage. So we begin by assuming like this. So I1 means the current in the first branch is the voltage on this branch divided by R1. This is Ohm's law. From Ohm's law, we know that the current in this branch is the voltage in this branch, the voltage across this branch divided by the resistance of the branch. So for I2 also V over R2, for I3 V over R3, for R ins, for I ins V over R ins. So we have V in common from both sides, so we take V as a common also from this side. We divide both sides by 1 over V, so the V is cancelled out by V. The R equivalent is 1, the 1 over R equivalent is equal to 1 over R1, 1 over R2, 1 over R3 up to 1 over Rn. If you have only two, if you have only two resistors, two parallel resistors, so R1, R2, so we have V, so the equivalent resistance will be 1 over R equivalent is equal to 1 over R1 plus 1 over R2, 1 over R2, sorry. So in order to calculate, just we can make elementary calculation principle, so which is R1 times R2 over R1 plus R2. This is the way to calculate two resistance which is in series. So this is the formula for two resistors which are in parallel. Their equivalent resistance is their product divided by their sum. So the equivalent conductance of the resistor in parallel is, we know that conductance is the reciprocal of the resistance. So the equivalent conductance is depicted by G. So the equivalent conductance of resistors or conductor connected in parallel, the equivalent is found by adding the individual component, because we know conductance is the reciprocal of resistance. So this is how we can calculate. The next concept is about current division. So the current I total is divided between these two resistors in inverse proportion to their resistance. The current from the I total is divided between these branches in inverse proportion to their resistance. The higher the resistance, the lower the current. The lower the current flows in that branch. So the current is shared by these resistors which are set in parallel in inverse proportion to their resistance. Whereas the voltage drop across resistors set in series, the voltage is shared or dropped in accordance to the resistance. The higher the resistance, the higher the voltage drop across that resistor. So the voltage drop is directly proportional to the resistance value. The higher the resistance, the higher the voltage drop across that resistance when they are set in series. But in the current case, the higher the resistance, the lower the current flow through that resistor. So the I1 is calculated by R2 over R1 plus R2 times I total, whereas the I2 is R1 plus R2 times the I total, the current from the supply current I total. So as you see, it is the inverse, you know. For I1 we take R2 as a numerator, for I2 we take R1 as a numerator, because the current, the share of the current across through that branch is inverse proportion to the resistance. That is how the current division is that is how the current this is known by the principle of current division. So now we're gonna see extreme cases. Okay, now we're gonna see how current behaves in extreme cases, when the circuit is open circuit and also when the circuit is short circuit, how the current division is calculated in these two extreme situations, as you see on the left side circuit. As I said, when it is open circuit, the whole current will flow into the I1 branch or the first branch, and no current will flow through this branch, because, as I said, current always chooses a path with the least possible resistance. So in this case, when it is short circuit or connecting wire, the whole current will flow into this path and no current will flow in this branch. Why? Because we can prove it from the formula. As you see, I1 in this case, I1 is simply inserting R2 is equal to 0, because short circuit can be assumed into 0. So inserting 0 and 0 right here. So we will find I total times 0 over R1. So 0 multiplied by any number give us 0. So how about I2? I2 is simply, for calculating I2 is R1 I total over R1 plus R2, isn't it? So assuming R2 is equal to 0, when we make R2 is equal to 0, R1 is cancelled by R1. So I2 is equal to I total. So when it is short circuit, I2 is equal to I of total. This is how it works. So this concept is applicable when we solve pragmatic problems. So we're gonna solve some pragmatic problem in the later section, and thank you for your attention.